So Faraday's law of induction. So first point is, if there is a change in magnetic flux linked with the coil, then an EMF induces in the coil. So here you must note that the magnetic field should be varying magnetic field, okay? Not a uniform magnetic field, not a non-uniform magnetic field, but a varying magnetic field. Otherwise, if the magnetic field remains same, there will be no change in magnetic field, so no electric current induces, okay? So due to this varying magnetic field, current induces inside the coil, okay? And according to Ohm's law, you can always write E is equal to IR. So eventually we will get this EMF. Okay, this is our induced EMF. Now second point. So what is this second point? So the magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. Let's say this is our coil. So the statement is this: the magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. So what does this mean? It means that EMF, which is dependent on time, okay, it is given by differentiation of our flux, because that is what this definition is talking about. The magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. So as soon as you apply a time varying magnetic field, okay, it will induce electric current inside the loop, okay. Due to induced current, we will have induced EMF, okay. So that induced EMF is directly proportional to, or you can say equal to, negative derivative of magnetic flux. Very important result, okay. So this negative sign indicates that the direction of induced EMF and hence the direction of induced current in the loop opposes the cause of its generation, which is in accordance with Lenz law. Now, what is Lenz law? That we'll discuss later, okay? But you first understand this, that let's say here magnetic field was in this direction. So electric current will produce in this manner, that due to that electric current, that induced electric current, it will produce magnetic field opposite to that external field, okay, to oppose that magnetic field, okay. So that way electric current produces to oppose its cause. This is called Lenz law, okay. We will discuss it, okay, just after this topic, okay. So let me write this statement here. Negative sign indicates that this induced EMF is opposing whatever external magnetic field there is, which is causing it, I mean, which is responsible for induced current, right? This induced current will produce magnetic field, and that produced magnetic field will oppose this external magnetic field. And why this happens? This happens due to energy conservation law. Okay, that is basically Lenz law that we will discuss later on. Okay, so we can write this EMF as minus delta phi over delta t, which is negative of phi 2 minus phi 1 divided by t2 minus t. Okay, and let's say if there were n turns inside the coil. Okay, so you can write this EMF this way, n multiplied by d phi by dt. Now let's understand Lenz law. So what is Lenz law? So the direction of induced EMF and hence the direction of induced current in a closed circuit. Let's say this is our closed circuit. Okay, we can take any closed loop, right? And let's say here the external magnetic field is inside the plane, inside the plane, or you can say inside the page. Okay, so this external field will induce electric current. Okay, inside the loop, right, in such a manner that due to this electric current, as you can see, it is anti-clockwise, right? So basically making it as a north pole, right? So due to this current, we will get a magnetic field out of the page. Are you getting my? So this magnetic field will oppose this external magnetic field. Okay, its cause. Let me write this in words. The direction of induced EMF just a minute. The direction of induced EMF and hence the direction of induced current in a closed loop is to oppose the cause due to which they are produced. This electric current was produced due to this external field. So this induced current will produce magnetic field which will eventually going to oppose this external field. Okay, basically opposing its cause, its source actually. So if the flux is increasing, induced EMF and hence induced current will try to decrease the flux and vice versa. Okay, this law is based on energy conservation law. So let's say you are bringing a bar magnet towards this coil. Okay, So what will happen? Let's say this is north pole, this is south pole. Now you are bringing this bar magnet nearer to this coil, right? So its magnetic field lines will pass through this coil, right? Eventually creating an electric current inside the coil, right? So this induced current will produce what pole here? It will produce a north pole, okay? It will going to produce a north pole to oppose this external field, okay? We know that north actually opposes each other, right? So as soon as you bring this bar magnet closer to the, you are bringing this bar magnet closer to the coil, this induced current will, I mean, it will produce a magnetic field in such a manner that this side of this coil acts as a north pole, as to oppose this external bar magnet's motion, okay, or external bar magnet's magnetic field. Now let's say you are receding from this loop, okay, you are going away from this loop, let's say. Now you are going away from this loop. Let's say this was north pole and this was south. So what will happen? You are actually going away, right? Flux is linked with this coil. So what will happen? This electric, here in this loop, electric current will produce, right, due to this residing motion of this external bar magnet, right, or this due to this external field. So it will generate a current in such a manner to attract this bar magnet, okay, to attract this bar magnet, okay. So it will produce a south pole here, okay. So it is anyway opposing its cause, okay. Here bar magnet is source, was the source, right? This was the cause, yes or no? So this bar magnet was want to get closer to this coil. So at that time coil was like, no, don't come near to me, right? And here in second case bar magnet is actually want to go, it is going away from the coil. So now this coil is like, don't go away, okay, that way. Initially, bar magnet was trying to get closer to it, so it produced north pole to oppose its motion. Here, bar magnet is going away, so it produced south pole to actually attract that bar magnet. Okay, understood? So this is the Lenz law. Okay, what it is again? The direction of induced EMF and hence the direction of induced current in the closed loop is to oppose the cause due to which they are produced. This law is based on energy conservation. Understood? Now, let's understand methods to change the magnetic flux.